I'm agora Lovecruft. My pronouns are they, them. Once upon a time, I was a theoretical physicist, specializing in quantum and string cosmologies, but one day a fairy princess came and kissed me on the nose, and the curse was lifted. Or I was doubly cursed, because now I'm a cryptographer. There's this thing which happens sometimes when I tell this to cute people at parties. They get really excited. Their eyes open wide, and they open their phones to show me their Insta profiles. I'm usually confused at this point, and then they ask if I'd want to do a shoot with them. This is when I realize that they probably misheard me, and they probably think that I said I was a photographer. At this point, my strategy is usually to enunciate very clearly and tell them, no, sorry, I'm not a photographer, I'm a cryptographer. I bend maths to my will to keep secrets. In all cases but one, however, this led said cute person to dismay, usually shuffling off, mumbling about tech workers. I mean, fair. My new strategy is to talk about my photography, which, albeit clearly second rate, doesn't seem to horrify folks as much as my other more mathy interests. But today, I'm going to talk about the truly horrifying. Not only am I going to talk about cryptography, but I'm going to talk about post-quantum cryptography. That is, cryptography which can be executed on a classical computer, but remains secure even against hypothetical adversaries in the hypothetical future where we hypothetically have ideal quantum computers suitable for generalized computation. Not only am I talking about post-quantum cryptography, but I will also be talking about 8-bit computers. How many of you had one of these machines as a kid? Woo-hoo! I didn't. By the time I realized I desperately wanted a Commodore 64, I was in kindergarten and the year was 1995. I begged my parents for one. My parents, by the way, are both hackers, for background. Around that time, I'd only written a little bit of shell scripts on an ancient DOS machine they let me use. My dad had to pull down an old VCR to store from atop a spare television and hook it up to the DOS machine to store my code on VHS magnetic tape. He said it stored more and would last longer. I had my own modem, which, being a little kid and too young to realize I could just desolder the modem speaker, I used it underneath a pillow late at night in order to sign into IRC. My parents argued which real language I should learn first. My dad argued for assembly, get to know the machine, the lowest bare metal workings of the hardware, before working up to higher level stuff. My mom argued for Perl. I don't know why. I looked at a bunch of samples of code in various languages. I had nothing else to go on. And of course, I chose Lisp. My parents asked me about it, and I told them I picked it because it was cute, since the trailing parentheses were curvy, like girls. They were mortified. It was that year that I first asked for a Commodore 64. They laughed and said, "You don't want one of those. We're going to get you one of the new Pentium Pros that are way better." I said, "Okay, sure, but I still want a Commodore 64. Since then, I've always asked for one, every birthday, every holiday. And they just kept saying, "You don't want that, it's old, it's junk." And this continued into my 20s, where at some point I moved to the EU. I stopped asking for anything because of the daunting prospect of having to carry more luggage across an ocean again. But a couple years ago, I moved back home to San Francisco. I mentioned to a friend how badly I'd always wanted a Commodore 64, all the kinds of art and chiptunes I'd thought about making with it, and maybe I'd even try making a game. My friend responded, "Isis, you could just, get one? You're an adult now." This was a revelation. After thinking it through, I decided my friend might be right. Surely, I was an adult. So I did what adults do on a random Tuesday for no special reason at all. I opened up eBay and I bought a Commodore 64. I texted my mom on Signal as soon as I got it to tell her the good news. She responded in all caps, "What?" This was very confusing to me. So I said, I've always wanted one. I've been asking for one since I was like 5. And still in all caps, she responded, "Sweetie, we thought you were joking." I can't even remember what the code I wrote last week does without documenting it extremely well, and my parents can think that I can keep a joke running for 22 years. So the MOS 6502 chipset, which is the chipset in the Commodore 64, was introduced in 1975 and sold for less than 1/6 of the price of the competing chips from Motorola and Intel, leading it to be credited, along with the Zilog Z80, for sparking the home computing revolution of the early 1980s. These chips were used in a large number of devices throughout the 80s, including the Atari 2600, the Atari 8-bit family, the Apple II, the Nintendo Entertainment System, including the Famicom Family Computer. I had no idea these existed. The Commodore 64, of course, the Commodore PET, the Atari Lynx, the Ohio Scientific Challenger 4P, the BBC Micro, and even Tamagotchis, all using the 6502 or variations of the basic design. The Commodore 64 claims to be one of the most popular home computers of all time, selling over 19 million units worldwide. I'm not sure if that still remains the case, but we'll let them have it. For the 6502 architecture, there are 151 8-bit official opcodes. An opcode is simply a number in machine language that a processor recognizes as being a request to do a specific operation. These 151 opcodes are organized into 56 instructions, some with multiple addressing modes, which I'll get to in a second. Instructions are then named with human memorable names called mnemonics, which is what we use to write assembly languages. The first so-called page of memory, which is not actually a page in the modern sense, but rather a contiguous chunk of 256 bytes, which is easier for the processor to successively address on these chips, is referred to as the 0 page. The chip which was actually used in the Commodore 64 is a 6510, the only difference being that the first 2 bytes in memory on the 0 page of the chip allow what is called bank switching, where you may memory map or unmap hard-coded ROMs or allow addresses to pass through into RAM. The ROMs on the Commodore 64 include the kernel, some I/O functionality, a thing called a character ROM that literally just stores characters and glyphs, and the basic interpreter, which is a text adventure that people seem to enjoy in the 80s. One important thing to note, however, as it's an 8-bit processor, the registers are 8 bits, and you only get 3 of them, A, X, and Y. A is called the accumulator. It's what most of the instructions operate on. So when you tell the 6502 to do something like ADC #5, which stands for add with carry, the literal number 5, it does an add with carry of the immediate 5 to the contents of the accumulator. The other 2 registers, X and Y, are sometimes referred to as index registers. As the name implies, they are generally used for storing indexes and can only do incredibly basic tasks like being incremented or decremented or being transferred to another region in memory. So now onto addressing modes. So this is immediate addressing. So the first instruction you can see is LDA, which means load A, or load into the accumulator. The literal, that's what the hashtag stands for. The literal hex is what the $ stands for, C0, which is the number 192. And then we clear the carry flag. The carry flag lets us know if there's been an overflow in the accumulator. And then we do add with carry, the literal number 5. Now the accumulator contains the number 197. This is a pretty straightforward mode of addressing. So now we can see the same instructions again, but used with absolute addressing, where we use absolute addresses to point to a certain region in memory. Again, we load the number 192 into the accumulator. We store it at the region in memory, C, F, 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 3 Fs. We load the number 5, the literal 5, into the accumulator, clear the carry bit, and then we add the contents of the address in memory at CFFF into A, and now A again contains 197. Next mode is a little bit more complicated, and this is where things start to cause problems. You can quickly write code that does surprising things. We load 0xFA into the accumulator. We store that at the location in memory CAAA, and then we load CF into the accumulator. what we're doing here by loading these literals 0xCF and 0xFA is we're putting an address at another address. But because the accumulator is 8 bits, it can only store 1 byte at a time. So we have to do the topmost bits first and then the bottommost bits second. So we're starting the bottommost bits CF at CAAB, which is the next byte in memory, obviously. It's 1 up from CAAA. And then we're loading the number 5 into the accumulator, storing it at CFFA, loading 192 into A, storing it at CFFF, clearing the carry flag, and then we do the add at CFAAA, which gets dereferenced to CFFA, and then you take the contents of CFFA, which is 5, is 192, and we load it into the accumulator. A, again, now contains 197. And I promise this is the last one, but this is where things start to get really, really weird, and you can cause bugs really quickly, which is amazing. So again, we're doing this whole setup of loading 0xCFFA into the spotted memory at CAAA. We're loading 5 into the accumulator. We're storing it at CFFA. We're loading 192 in the accumulator, same thing as before. We're storing it CFFF, that's the same. We clear the carry flag, but now we do indirect indexed addressing, whereas we give it an address where it's going to add an index to it first, then look at the location in memory to find another location in memory, then take the contents of that memory and add it to the accumulator. A now contains 197. As you can guess, this is a really quick way to cause bugs. So indirect mode is one of the ways that it's sort of fucky, is that it has no carry flag associated with the jump instruction. So it's really easy to transfer program execution to the wrong place in memory by using indirect indexed addressing mode and giving it the wrong index, because suddenly if you're at a page boundary, say you're at 30FF, it doesn't actually wrap around to grab the next address at 3100, but it wraps back around to 3000. So suddenly you've transferred program execution to another place in memory which you didn't intend, which is really hard to debug, and I will show an example of that. So we load 40 into A, the literal 40, and we store it at 3000, as I mentioned. We load 0x80 into A, we store it at 30FF. We load 50 into A, and we store it at the location in memory 3100. So you would guess that if you jump to 30FF, it would grab the next byte at 3100, and you would transfer program execution to the address at 5080. That's not the case, because it wraps back around. You jump to 4080, and now you have a horrible bug. So now that we understand a little bit about the assembly, to talk a little bit more about the opcodes. So because the opcodes are 8-bit, there are obviously 256 available opcodes, meaning that there are 105 which exist but are unofficial, otherwise often called the illegal opcodes. Many of them curiously combine other arithmetic operations, such as ORing the contents of a register before shifting right or left by the value stored in another register. Obviously, it's important to use as many of the illegal opcodes as possible. It may even be illegal not to use as many of the illegal opcodes as possible. Sadly, though, I have yet to find a place in my current code to use any of them, so I'm leaving this as an exercise to the reader. Patch is extremely welcome and will be rewarded with a lapel badge which reads, "Be gay, do crime codes." All right, so now that we've covered the 6502 or 6510 chipset a little bit, I'm going to talk a bit about the cryptography. So hypothetically, in the hypothetical future, we will hypothetically have hypothetical ideal quantum computers, which are hypothetically suitable for generalized computation, and which hypothetically have suitably efficient hypothetical quantum error correction codes. Hypothetically. If this were to hypothetically happen, it would ruin most of our current, often discrete log-based public key cryptography. Some, like myself, believe that efficient quantum error correction is likely impossible, and even if it were possible, that we're more likely to see non-generalized quantum computers designed to break only certain classical cryptographic algorithms, or even a certain set of key pairs for a certain classical cryptographic algorithm. Even if the worst case scenario is a remote chance, it's still only, even if it's only 0.0001% likely outcome, it's nonetheless important to prepare for, as any enciphered communications recorded now could later be deciphered by a quantum-capable adversary. As mentioned before, the subfield of cryptography, which deals with algorithms which can be run on a classical computer but withstand attacks from a quantum computer, is generally referred to as post-quantum cryptography. The essential reason why hypothetical quantum computers will be better at certain classes of mathematical problems than classical computers relates to the complexity of a function called the Fourier transformation. Basically, the Fourier transform takes a set of combined waveforms and breaks it down into individual components. A real-world example of this would be taking a recording of a group of people talking at a party and breaking it down into recordings of distinct individuals. Fourier transforms are phenomenally expensive on classical computers, reaching exponential complexity in the number of distinct input waveforms, but the quantum Fourier transformation is linear. This allows us to compute certain classes of problems faster on a quantum computer than on a classical one, such as computing discrete logarithms and factoring composites of large primes, mathematical problems which much of our current public key cryptography relies upon today. So before delving into the post-quantum variant of this, let's review classical elliptic curve key exchanges. We set a publicly known point, G, a generator of a group of elements, that is, points on the elliptic curve. This group has order P, which simply means that there are P number of elements in the group. Alice and Bob both choose secret scalars, which are simply integers modulo some prime number, as A and B in the set of integers modulo that large prime number. Alice computes her public key as big A equals little a times G and sends this to Bob. Similarly, Bob computes his public key as big B equals little b times G and sends this to Alice. Alice computes their shared secret as S equals little a times big B, which is equal to little a times little b times G. Bob computes theirs by S equals little b times big A, which is equal to little b times little a times G, and thus they arrive at the same shared value, and only an adversary who can break discrete logarithms in real time, such as a hypothetical generalized quantum-capable one, is able to take their public values in real time, derive the secrets, and arrive at the shared value. So, without going into much of the details of the mathematics, but feel free to talk to me later if you'd like to know more. To make this problem secure against adversaries with quantum computers, we need to rely on different mathematical problems. In the case of supersingular isogeny key exchanges, which that's a lot of big words, I'm gonna kind of gloss over them, rather than using points on elliptic curves as public keys, we use the elliptic curves themselves as public keys. By computing what are known as isogenies, that is, one-to-one mappings where each point on a curve uniquely corresponds to a point on another curve, and vice versa. So back to 8-bit. The catchphrase for the Commodore 64 was, "I adore my 64." People genuinely love these machines, and I do too. And if we're going to continue using them, it's vital that we secure Commodore 64s against attacks from quantum computers today. So, one of the best known sets of parameters for implementing supersingular isogeny key exchanges requires implementing a specific field, essentially a set of numbers which have both addition and hence subtraction, and multiplication and hence division defined. In this case, the field is integers modulo this 434-bit prime. Commodore 64s have 8-bit registers. Modular arithmetic, 434-bit prime. So typically in cryptography, we assume some things about the chips we're working on. We assume typically that they have a multiplication instruction. Not only they have a multiplication instruction, but one which operates in constant time. The term constant time is slightly misleading. We don't mean always runs in the same amount of time, but rather we mean doesn't change the amount of runtime with respect to secret data. Algorithms which are not constant time, also known as variable time algorithms, have numerous known attacks for recovering secret values while running such algorithms, such as listening to the frequency of a whine that the CPU makes, watching latency over a network or through a coprocess, or watching to see if some junk data has been evicted from a CPU cache. So now not only do we assume we have a mul instruction, but we generally assume very specific things about the way its underlying algorithm works. This is where I should point out that the 6502 or 6510 chip architecture in Commodore 64s not only has no constant time instruction for multiplication, it has no multiply instruction at all. None. So if you want to multiply numbers, you have to implement it using bitwise shifts and addition, and manually handle the carry flag. To my knowledge, no one has ever attempted constant time cryptography on such an architecture. So I sat down to a blank Emacs buffer, staring, for about 20 minutes. And then, like every normal, completely rational developer does, I decided to see if anyone else had ever tried solving my problem before. I did this knowing full well that I was doing something that explicitly had never been done before. And I opened up a new tab, and I went to Google, and I typed in the query, big number, small computer. This went about as well as you can expect. So I sat down again and began to implement from scratch 448-bit integers of 56 words each, modulo a 434-bit prime on an 8-bit system. You know, like a completely normal, rational developer does. So at this point, I have bad news. I brought my Commodore 64 today. I intended to do a demo of the code, but at this point, the code is not quite yet finished. I've been working on it for like 2 or 3 weeks now. The code is on GitHub. I do have the finite field arithmetic done, and the Montgomery arithmetic largely done. What's left is to implement the 2 isogenies and 3 isogenies, which are comparatively high level, and they sound like big words, but they're actually easier than implementing the field, which involves implementing multiplication, which is not fun. Honestly, I was hoping to demo it live, as I mentioned, because by my estimations of the cycle count from what I have done so far, I believe Alice's key exchange should take a brief 40 minutes. And Bob's side of the key exchange should take roughly an hour, just in time for the end of this talk. That's all. I would like to thank Bang Bang Con for inviting me, and thanks to the organizers for their hard work, and thank you to all the other wonderful speakers whose talks I am looking forward to today, and solidarity with the graduate students on strike.